Hey, everybody. Mark, tell me when I'm good to go. Yeah, good. Hey, everybody. Welcome to another Fullstack speaker series. Tonight, I'm really excited to introduce Joel Kemp. Joel is an engineer at Behance and Adobe. Do you know one of our students there, Ash? You know of him, but not.
Yeah.
Okay. So he works at Behance and Adobe, and he came. He proposed a talk topic on their build process there. And all of you who are using FSG or who will be using FSG are familiar with using Gulp, different build tools. What we don't understand is that what we hope you understand is that as you get more complex projects, larger teams, these things become very important in how they keep the team organized, keep the team moving quickly. And so it's an important part of the engineering process for us all to understand. So I'm really excited tonight to have Joel talk about the build process at Adobe and walk you through the narrative of how the build process has changed and evolved over time as the team's demands have changed and evolved. All right. So without further ado, Joel, take it away.
Thank you. Thank you. So I am talking today about parallel uglification and some of the work that we were doing at Behance some time ago that still needs some further work to make it just better these days. So I'll give you a little bit of context on that. I'll be pointing at some of these. Behance is broken up into two separate flagship applications. One is Behance.net, which is a social network for creative professionals who want to upload their work and get discovered. We have a new application that we just recently released called Adobe Portfolio. And so the network is using Require.JS and Grunt, which are somewhat, I guess, old school technologies these days. Portfolio is using somewhat of the new hotness, which is Webpack and Gulp. And so I won't be talking about Webpack and Gulp, although the concepts do apply. They still hold true for whatever runner you're using and whichever module loader you happen to be using. So just to frame a little bit of the sheer scope, the sheer size of the code base that we're dealing with on Behance.net, we have about 1,000 plus modules. And by module, I mean a JavaScript file, a file that contains some bit of logic that represents a particular portion of a page, or let's say the entry point to an application. So that's what I mean by module. And those 1,000 plus modules end up getting assembled into 75 plus different bundles. And so there's a lot to talk about there. We abide by this architecture that is not a single-page application. In a single-page application, what you'd roughly do, and if you have a smaller project, you would have one massive bundle that has everything about your site. And so users don't refresh, pretty much. They are just navigated to new experiences within your application. And all of that code, again, is typically bundled into one big application, or one big bundle, one big JavaScript file. The issue there is that as your code base grows and grows and grows, that bundle just continues to grow as well. And the users are downloading this bundle. And so bandwidth is pretty important. You don't want a user to wait forever to download the bundle, to then have JavaScript executed, and then there's a lot to say on single-page applications, which I don't have time for. But when you have JavaScript executed, typically the JavaScript will say, OK, well, where am I currently? Oh, I'm a new user? Then I'll go talk to the backend and get the data that I need to render my first page. And the user is just waiting while all of this is happening. And so typically you just see a white screen, which is a terrible experience. And so that's a different story of single-page applications and where they go wrong. But for Behance, we don't want a gigantic bundle. So what we do is we segment our website into particular features or applications. And so we have some server-rendered pages that will launch a JavaScript bundle. So each segment of our application has a particular bundle that it cares about. And that way, a user that goes to the profile page, for example, loads up that profile bundle. The profile page doesn't care about what's going on the settings page. It doesn't care about what's going on the discover page. It doesn't need any of that JavaScript. And that keeps the site pretty much scalable in the long term, but also performant. So that explains how we ended up with about 75 plus bundles. It's a massive, massive website, massive code base. So a year ago, I was talking about this problem that we had, which is the process itself relied heavily on Require.JS. How many of you are familiar with Require.JS? Okay. So Require.JS is a module loader, which is a separate discussion on what module loaders are really good for. But I am inclined to talk about them briefly. So let's do it. So module loaders are really, really interesting and really essential. I've been on projects where we don't have module loaders like Require.JS or CommonJS with Browserify or what have you, where you have your application logic spread across all of these separate files, and somehow you have to deliver them to the user. And the way you do that is by having script tags on the page within index.html file or what have you. But you end up with this problem very, very quickly, which is this particular module depends on this other module having been run, executed, done some work. There's an order dependency. And how do you guarantee that this module loads before this one does? Well, again, we go back to our index.html file, and we have script tags. And so you would reference all of your files with script tags. And the larger your application gets, the more script tags you have. And we had maybe like 100 script. It was really bad. We had 100 script tags that we had to manually maintain. And if the order dependency at all changed, you had to go and figure out like, okay, well, maybe I do this and rearrange this. And it would potentially break. It would most often break. It's just a really bad way of doing things. It's a bad way of managing your application and order dependency. And then module loaders came around. And JavaScript is funky in that it doesn't actually have a native import mechanism. So you can't natively establish or declare that this module here depends on all of these other modules and then have the browser resolve that for you. It doesn't work that way. And so tools like Require.JS came about to implement the AMD module format specification. And regardless of what the syntax looks like for that, it's a way of saying, I am defining a module that has these explicit dependencies. It's a way for you to say that I depend on this other module's existence. And you architect your code base that way. And so now you say, OK, Require.JS, here is my entry point. And it's going to say, all right, well, that entry point defines dependencies. And those dependencies, let me go resolve them now. Well, for each dependency, it declares a set of dependencies. And what you're effectively doing is traversing this tree of dependencies. You're forming this dependency tree. And that's taken care of for you. No more script tag juggling. And that's where module loaders shine. So Require.JS is a module loader. Good? Awesome. So, OK. So we're using Require.JS. And Require.JS is great as a module loader, but it has a hiccup here, where in development, when you have a module that's being loaded that has dependencies, it will go and asynchronously request those particular JavaScript files. We don't want that happening in production, right? These requests are expensive, and it slows down the user experience. So the natural way of solving that is to concatenate all of the dependencies within that dependency tree. You concatenate that into one file. That is a bundle. The process by which Require.JS goes about assembling these bundles, it uses a tool called the optimizer, RJS. Okay? So that's specifically what I'll be talking about in this particular talk. It's RJS and how RJS traverses dependency trees, assembles bundles, and there's another step after you assemble these bundles. There's the minification step. You guys have heard of minification? So minification is a technique that saves bandwidth by obfuscating your code, by condensing variable names into single letter variable names, by eliminating white space, by doing all of these sorts of transformations that minimize the amount of space your code takes. Smaller amount of space, less time it takes for a user to download your JavaScript. Win-win. But uglification is so minification is achieved by uglification. There's a library called uglify.js, and that's what's used to minify code. Uglification is a really, really expensive operation. So what we're dealing with here is assembling a bundle, and then minifying that bundle. Natural steps necessary to ship code to a user. Essential steps, at least for now. There's a lot of talk about HTTP2, which you can look at. You can Google around and try to read up on that. It's pretty much what's coming, which in theory is supposed to eliminate the need for this concatenation, minification step. In any case, we're not there yet, so we still have to worry about this. And a year ago, we were dealing with a build process that took about 2.5 minutes to assemble all 75 bundles plus and also minify them to get everything complete, ready to send to the user. Well, 2.5 minutes doesn't seem too bad, except for the fact that when you want to ship code at Behance, you would run that process for building out to stage. And so we have a staging site, which is not production, but very production-like. And so users don't have access to that. It's only really for internal use. It's so that we can manually test that we didn't break anything, right, outside of local development. So it's almost a pre-production. So we have to build out to pre-production, and then we go on the site and we manually make sure that we didn't break everything, that everything is okay, our feature is good. And then what we'll do is say, okay, we're ready to build to production, and we'll start that whole process over of reassembling all the bundles, reminifying everything, and then shipping that off. There are optimizations that you could do there naturally, right? Why not just move those files over the already minified, already concatenated bundles? But bear with me on that. So that 2.5 minutes doubles effectively because you're building to all these different environments. And with the optimizations that I'm going to talk about today, we managed to get that down to about 55 seconds, which is pretty huge. And you have to imagine, we want developers to ship code as quickly as possible. The fact that they have to wait 2.5 minutes per environment, then have the manual testing and so forth, creates so much delay. It was taking us maybe 30 minutes, 45 minutes to actually ship our code between environments all the way to production and verify that everything was okay. That is a lot of time for what's effectively a small change, or what should be a small change. So we needed to shave some time off with this process wherever possible. Fast forward to today, and we're at 5 minutes. And so we're sad. Things are not as good as they were a year ago. And I'm not going to talk about solutions for that because we still have the 5 minutes today and we have to fix that somehow. And I don't know what's causing that, but I will at least hint at some of the problems that we had about a year ago and some of the techniques that we used to fix those problems. So in our old process, we still used RJS. We, to this day, still use RJS for Behance.net. RJS would do a couple of things for us. It would transform images to CSS spreadsheets. It would go about tracing all of the entry points. So what we have is a build configuration for RJS, and we say, hey RJS, let me tell you the entry points to all of these bundles. RJS says, cool, thank you. Just tell me you want to build. I'll go ahead and traverse all of those bundles that you've explicitly declared. I will then trace out the dependency tree, concatenate everything, and form a bundle. So that's the generate.js bundles portion of it. And then we also let RJS do the uglification for us using uglify.js too. And so what it would do, the serial process was, you have already predefined a configuration for RJS. You've listed out all of the bundles explicitly, so 75 plus, yes, we've done that manually. And you then execute this process. RJS says, okay, let me go look at that list of bundles. And for every single bundle, traverse the tree, and then do that for every single of the 75 bundles. So that's a serial process. It does it one at a time. And then after it's done with all of that, once it's assembled all of the bundles, comes the uglification step, the minification step. And so what it does is, again, in a very serial fashion, it will go across all of the now bundled 75 files, and it will uglify them one at a time. There are many, many problems with this. So that's what the old process was.
Hey, Joel.
Yeah.
Can I ask a question on this page?
Sure.
So when you say the JS bundles, you're referring to a bundle for profile page.js,
yeah.
account page.js.
Yes.
Now, if you look at all the bundles and then how much overlap would you say there is? Like if you take all the bundles and add them up, their size versus just the raw file size of the files themselves, like how much do the JS bundles create a lot of overlap? And so account page.js requires like profile image.js, but so does this thing. Like how much do you repeat yourself in this process?
So I don't have exact numbers. One, you're hinting at the inherent redundancy about dependency trees. And especially when you have core frameworks or libraries, every single feature is built on top of those. And so they naturally will be or could be in every single bundle. And so how do you go about pruning those trees, reducing the redundancy about them? What we've done is establish a common bundle, which gets around this problem by saying, well, here are pretty much all the things that are common to many of these bundles. And so preload them off into their single bundle called common. And then in the build configuration for the other 75 bundles, what you're saying is, well, exclude common, exclude all of the files that we've dictated are in that common bundle. And that way you've effectively reduced the redundancy there. And every bundle still works properly because by the time that they're trying to resolve their trees, the common bundle has already been executed potentially. Right? And so the core framework library layers have already been resolved. They already exist in the runtime environment. Then your bundle comes around and everything's there. So I don't have the exact percentage of, like, given a bundle, what is the natural redundancy before the common bundle, but we do have a solution around that. So we're thinking about how do we make this faster? The bottleneck is clearly uglification. 27 seconds for generating bundles is, it's not too bad. We've identified the bottleneck and we should optimize there versus a premature optimization on generating JS bundles. So we're thinking about how do we go about doing this. And uglification was again the bottleneck. Bundles are really big, and the bundles vary in size. One particular feature on the site could be huge. The Discover application is rather large. It is the entry point to Behance.net. It shows so many images. It allows for all of this complex filtering. It's a beast of a bundle. And there are others across the site that are also rather large. But there's also redundancy. And you could accidentally bundle in a very, very large dependency like jQuery. Or we use a text editor called CKEditor. Any sort of large vendor file, if you accidentally bundle those in, you end up with massive bundle that then has to be uglified. And uglification, the way that it can really save you bytes is by formally analyzing the entire source code, determining how it might, in a global sense, optimize that file, and then generating a new compressed file from that. So the higher up it goes to look at your code, the better off the optimization. And that takes a very, very long time as your bundle grows and grows and grows. So that's why uglification was really, really slow. So we thought about, what if we bring uglification optimizations, namely somehow parallelizing this process into RJS core or Require.JS core, and it introduces a bit of complexity that core didn't want. Core also allows you to say, oh, RJS, I don't want you to handle uglification. I only want you to do the dependency tree tracing and the bundle concatenation. That's all I want you to do. And so, rightfully so, it was, well, build your own tool and then just pipe those bundles into your own uglification process. So we created a tool called BeUgly. And BeUgly parallelizes the process. I mentioned that it's a serial process. It goes one bundle at a time, generates it, and then also minifies it. And so what if we split that workload? The bundles are pretty much independent of each other. And so what if we just had one core tackling a big chunk of bundles and splitting up the workload that way? It's naturally, because of these independent, the exclusive nature of these bundles, and that they don't really overlap to a point where there's any sort of conflict, we can parallelize this. So we use Node for this and built our own tooling called BeUgly. It's currently made for Grunt. No one has requested that it goes to Gulp, and we haven't had a need for it on Portfolio yet, which is using Gulp. Because Portfolio is rather new, it's not as massive, and it hasn't been around as long as the Behance.net application. But it could be extracted and made runner agnostic. So the first idea that we had for parallelizing this process of uglification is that we would do a very naive split of the workload. We know how many files we have. We have 75 bundles. What if we chunk that about all of the available cores? Just a nice even split. And say, hey core, you take this set of bundles, you uglify those. You core, you take this set, etc. And I'll just wait until you all come back and say that you're done. And then I'll move on with the rest of the process. And that's a very simple way of parallelizing this. The old uglification time, again, before this optimization was 2 minutes and 30 seconds. With this optimization of using multiple cores, it went down to 2 minutes. And we were just like, wait, that's not fast. It's parallel. It's supposed to be super fast. And so we were a bit disappointed by that. And we found that the major problem that was causing this not really, like, I guess, this slowdown effectively, is that you end up with this situation where one core just had the unfortunate luck of taking on some of the chunkiest bundles and having to uglify those. And so pretty much every other core is done, dead, and this one core is still chugging along trying to uglify these files. And that causes the entire process to slow down because you cannot proceed until all cores have finished. So it's a bit unfair there. One optimization that we could come up with that would alleviate this unfairness is to say, well, maybe I don't just distribute that 75 into chunks of 4. Here's what I'll do. I'll let you tell me when you're done, and I'll give you more work. So I'll start you off with maybe 1 or 2 bundles, let you do what you need to do, and I'll do that for every single core. You take 2 bundles, you take 2, you take 2. Oh, you're done? Here, take 2 more, and do that type of, not necessarily round robin, but sharing the load that way. What happens is that you minimize the chances of one core just chugging away, right? You're saying, well, if you happen to deal with these chunky bundles, everyone else can help pick up the slack. And so that didn't really give us too much of a gain. So we still had to figure out what was going on. And the issue there is natural to uglification. It's a global process. It looks at the entire source code, the entire bundle, and tries to optimize it. And that's what's taking so long. So the second idea that we had was, so optimizing bundles takes a long time. So what if we optimize the modules instead? What if we uglify all of the modules and then assemble the uglified modules into an uglified bundle? You guys with me on that? And that's pretty cool. That actually turned out to be really, really fast because we are saying, hey, uglification algorithm, you only care about a really small file now. And it does that really, really fast. The trade-off there is you're getting a subpar minification in that when you were dealing with a massive file, it was able to analyze the entire file and do one massive swoop of optimizations to really save you some space. When it only has a single file, it doesn't know about the neighboring modules. It can't detect similarities across those neighboring modules that were in its dependency tree. It only has a very, very small view of the world. And so it can only optimize so far. So you end up with a subpar minification. You end up with more bytes than you would have had in the global sense. What we also had was vendor files, as I mentioned, that were creeping into the bundles. And actually, vendor files are still chunky because typically jQuery is not a series of modules. jQuery is one really, really big file. And many of the vendor dependencies follow suit. And so what you want to do is not uglify those because they would take a while. So if you don't uglify those vendor dependencies, and they don't really change, right? You're not coding those. You're not working on them. You're not building new features into them. They rarely, rarely change. So why constantly uglify them? why not bring them into your application, hopefully pre-uglified? If not, then you have to host your own uglified version of those those vendor files. So you can cut out vendors, which leads to massive, massive savings. So uglify first was the main approach there, and it worked. Uglification of small files is really, really fast. Every module is uglified once, which is actually a bit of redundancy there. Is it? I guess for those modules that are not in common, because they weren't really common across all bundles or the majority of them, you would not include them in common, and so they would be redundant. And when you are minifying every single bundle, you are re-uglifying those modules that are common, right? That are redundant. And so your one module ends up getting minified many, many, many times, potentially. The ones in the common bundle are not. They're minified once. But there is redundancy there. And with the uglify first approach, though, every single file is uniquely minified only once. The cons, of course, being the increased file size, potentially increased file size. We found that it was 4K across all the bundles, which was nothing. 4K is, I guess an image is way bigger than that. So we just said, well, this is great. The payoff is that we get to ship code quicker. When we were relying on Require.JS to do uglification for us, we had all of these niceties in there, like dead code elimination, which is you can have these flags set up in your code. Let's say you want to do some sort of debug logging, like console logs. You don't really want to ship console logs to production because your users, well, first off, older versions of IE don't have console, and so you'll have, yes, they don't, and they will break because they're like console, I don't know, I can't call log of undefined. Yes, it's really bad. That's where the whole thing of don't ship console comes in, and then you end up with these, not even polyfills, but like this way of avoiding the error where you say like window.console equals window.console or some empty object, and that way when it calls log, in any case. So there are ways using Has.js, using these dead code elimination techniques, where you get to guard that console log with some sort of flag that says, am I in a debug environment? Am I in a dev environment? And at build time, it will say, well, you're not going to be in a dev environment in production, so I will actually delete that code from the generated bundle, which is pretty cool. That broke. So we had to fix that. And even though you parallelize this process, and this kind of comes to the problem we have today, which is even when you parallelize and you split the workload, what you're dealing with is effectively linear time. In that, as the number of files continues to grow, you have to hit every single file. Your process will touch every single file. So we'll have 1,000 now, we'll have 2,000, we'll have eventually 1 million. I don't know, maybe Behance will die by then, but you might end up with 1 million files. And you have to go ahead and process every single one of those. And so it's naturally linear time, which is the best that we can do, unfortunately. So there are limitations, and parallelization is not necessarily a quick fix, but it's just dividing that n by a factor, by like 4, really. In production, we have 8 cores, and it's super fast. But for our staging, we only have 4. So we were thinking about more optimizations, right? We got it down to 55 seconds, which was great, but we could do even better. Because when I mentioned the build process, we were dealing with 2 serial processes. One was the assembly of the bundles, the assembling of the bundles, and the other one was the minification of the bundles. Okay, again, RJS would go through each of the 75, build those bundles, then uglify was, let me go through each of the 75 and uglify. We've parallelized the uglification using beugly, but the serial process of assembling those bundles is still there, and it was 27 seconds, actually worse now. So there's work to be done. So we were thinking of some ideas, and we came up with this idea of be lazy. So be lazy banks on this feature of RJS, which says, hey, if you still have the remnants of the old bill lying around, then I'll use that and only rebuild bundles that need to or that have changed, in that part of the dependency tree of that bundle has changed, and so I need to regenerate the bundle, which is great because if you're shipping a change to your code, to your website, it's isolated to one of those bundles potentially, right? You're only modifying one feature. And so only that one bundle needs to get regenerated versus all 75. That's great, but we'll see that that isn't going to work for us. So be lazy is a great idea. But then there's also the vertical scale, in that maybe I shouldn't spend my time working on these cool optimizations. Maybe I should just pay more for hardware and get beefier boxes. That might solve my problem. So some of the hiccups with, let's say, Be Lazy, for example, is that we're using Docker on Portfolio. And we're not using it on the network, but we will use it on Behance.net. Docker containers don't live very, very long. You create a container, it runs, and then it gets destroyed. And so for every build that we do, we create this container from scratch, and then we destroy it. There are no remnants of the previous build. And so everything runs fresh every single time. And Be Lazy banked on having access to that previous build's output. And so Docker kind of ruins the day. Although I was talking to David, and he mentioned, what if you, in the Docker file, use that as a database of sorts and keep track of the previous state using the Docker file, which is what's used to spawn that new container, which would be pretty cool. So I'll think about that. We're using ES6. We used ES6 on Portfolio exclusively. From the very beginning, we were using Babel and ES6, and so now we're using Webpack as well. And we want to use that on the network, on Behance.net. But it's really old, and there's a lot of code there that is not ES6. It's only ES5. And it is not easy to bring ES6 code to such a massive application, unfortunately. So you have to somehow squeeze Babel into that pipeline of building out these bundles. But then you might also, you're writing your code in ES6, and so you need to transpile it before you use it in the browser for local development. So now you've introduced this local server that needs to run, and what's the relationship between that local server and your build server? Maybe they can share some of the workload. So there's an interesting series of opportunities that open up when you start to introduce ES6. Unfortunately, uglification.js, our minification library, it doesn't support ES6. So uglification.js implements its own parser. When I said that it formally analyzes source code, it uses what's known as a JavaScript parser. And so it will, you guys have done this actually over the weekend. You built your own parser. And so we have parsers in JS. There are some popular ones. Esprima is one really, really popular one. There's also Acorn, which is really, really popular. And Babel, have you guys heard of Babel? Yeah, so Babel has its own parser as well, which is a fork off of Acorn that's called Babylon. And so these parsers pretty much do the same thing in theory, which is take in a string, which is your source code. It will then tokenize it and break it into all of these parts, and it assembles a tree, which formally describes that program. And then it will do transformations on that tree to convert ES6 tokens into ES5 tokens. ES5 being the current standard of JavaScript, not, well, ES6 is now standard, but like the widely adopted version of JavaScript is ES5. So uglification.js doesn't use any of those parsers that are popular. Those popular parsers already have ES6 support. Uglification.js has its own parser, and so it has to re-implement ES6 in its own parser, which sucks. And we're waiting on that, and hopefully we get it soon. Babel, though, has a plugin for uglification, but it's fairly new, and the series of optimizations that it makes is perhaps nowhere near what uglification.js is capable of doing, since uglification.js has been around for a long time. It's pretty much the standard when it comes to minification. So ES6 throws a wrench in things as well. And as you develop new features, as you npm install or bower install this, bower install that, you end up introducing in all of these vendor files. And you have to keep in your head that, well, that's part of a dependency tree now. It's going to get uglified. And people forget. I mean, you don't want to think about this, right? A build process is completely separate from your development process. And so you end up slowly but surely having these massive vendor files creep in. And that's why we're sad today, because I'm sure there's some vendor file in there that is really, really chunky, and we just haven't blacklisted it yet, prevented it from being uglified. So there's some tooling that's potentially necessary so that we don't have to think about this anymore. Something that would exclude all of the vendor files, but again, also assuming that they're already uglified. Because even if you don't uglify them, they're still getting assembled in the bundles. They're still getting shipped to the users. If they're not uglified at all, then the users are paying that price, right? They're downloading a really meaty file that hasn't been optimized. And so now we as consumers of these applications or these libraries have to start worrying about, well, is that going to be used in client-side code? If so, is it minified already? It's just not really a standard thing. I mean, NPM is only now starting to be used for client-side code. It was Bower before. And I don't think there are established practices in terms of shipping minified code as the entry point to your library, your NPM module. So today, I pulled these numbers today. So for staging, to build out to staging, here's a breakdown of all of the steps. I didn't talk about copy all. It's not really relevant for this. I mean, it's 7.9 seconds, which is some cost, but not the biggest cost. Be Ugly is there running. I told you we're using it. And it's about 40 seconds, which is not great either. But again, I mean, let's chat. Let's talk about how we can make better. It's open source, by the way. And then Require.JS, 3 minutes and 47 seconds to traverse all those bundles and assemble, to traverse all of those entry points and assemble the bundles. That's a lot of time. We're waiting and doing that twice. Although, if you look at the production build time, because again, we're building the whole app again for production, it's faster. It's half the time. And we're just running the same stuff, right? Be Ugly is there, and Require.js is still there, but beefier boxes. And I guess I could be building features instead of working on this stuff. And so a beefier box is kind of a quick win, I guess. But that becomes really expensive. So there are optimizations to be made, and what stops us from working on it is that it's only 2 minutes and 6 seconds in production. And so it's not terrible, but it will get there. And then maybe I'll be able to work on it at some point in the future, right? Until then, that's kind of where we're at. That's how we use parallelization in Node to achieve a parallel uglification. That's some of the areas of, I guess, research for parallel assembling of bundles. And it's pretty exciting. I'd love to chat about it if you're interested. Thanks so much.
All right, if you have questions, I'd love to give you the